In Chapter 10, we're talking about correlation and regression, and we begin in this lecture video by learning about correlation. A correlation exists between two variables when the values of one variable are somehow associated with the values of some other variable. A specific type of correlation is a linear correlation, and that's the type of correlation that we will be focused on in this chapter. There's a linear correlation between two variables when there is a correlation between the two variables and the plotted points of paired data result in a pattern that can be approximated by a straight line. We could have a positive linear correlation. That's where the straight line that can approximate the paired data increases or goes up as we move from left to right. For example, if the x-axis corresponded to age and the y-axis corresponded to the amount of money in your retirement account, you would expect a positive linear correlation. As your age increases, the amount of money in that savings account also increases. We could also have a negative linear correlation. That's where the straight line that approximates the pattern of the data decreases or goes down as we move from left to right. So if our x-axis again corresponded to age, but the y-axis corresponded to energy level, we might expect that as our age increases, our energy level might go down, and that would be a negative linear correlation. The final option is to have no linear correlation. That's where the paired data cannot be approximated by a straight line. This doesn't rule out a different type of correlation. We're just saying that the pattern can't be approximated by a straight line. For example, if our x-axis corresponded to the amount of chocolate consumed and the y-axis corresponded to exam scores, we would not expect there to be a linear correlation. So how strong of a pattern does there need to be in order for us to say that there is a linear correlation? How close to being in a straight line do our data values really need to be on the scatter plot? Enter the linear correlation coefficient, R. R is the measure of the strength of the linear correlation between the paired quantitative data x and y values in a sample. If we're working with a population, the linear correlation coefficient is the Greek letter rho. R tells us how strong of a linear correlation exists. The values from R range from -1 to +1. Values for R that are close to -1 indicate a negative linear correlation, and values for R that are close to +1 indicate a positive linear correlation. And values for R that are not close enough to negative or +1 indicate no linear correlation. The closer the value of R is to positive or -1, the stronger that positive or negative correlation is. And we will use critical values to determine what close enough really is. Let's take a look at some other properties of R. Like we've already discussed, R is between -1 and +1 inclusive. One interesting thing about R is that if we were to convert all of the values of either of the variables to a completely different scale, the value of R would remain unchanged. R does not change, even if we change the scale of our variables. Also keep in mind that R is not designed to measure the strength of a relationship that is not linear. R can tell us the strength of a linear correlation, but it does not rule out any other type of correlation. R is also very sensitive to outliers. That is, a single outlier can dramatically affect its value. So keep an eye out for outliers when you're looking at scatter plots of paired data. Let's review some notation. N is the number of pairs of sample data. R is the linear correlation coefficient for a sample of paired data, while rho is the linear correlation coefficient for a population of paired data. There are some common errors that are made when working with linear correlation and the linear correlation coefficient. The first is assuming that correlation implies causation. Just because there's a strong relationship between two variables does not mean that one of those is causing the other. The second common error is using data that's based on average. We need to be working with raw single data values, not averages. When you work with averages, this can really inflate the relationship between the two variables and exaggerate the results. The third common error is ignoring the possibility of a nonlinear relationship. When we're calculating R, that can tell us that there's not a linear correlation, but that does not tell us that there's no correlation. There are different types of correlation that could be happening, and when we're calculating R and making assumptions about rho, we are only measuring the strength of linear correlation, not ruling out any other type. So let's talk about how we calculate R. R can be calculated by hand using this formula or using our calculators using the function linreg t-test, linear regression t-test. Keep in mind that with R, we will always round to 3 decimal places. Let's take a look at this example data and practice calculating R. The first thing we're going to do is put our data values into 2 lists in our calculator, list 1 and list 2, and we're going to be careful to keep them in the order that they are in because they are paired up. 5 corresponds to 6, 6 corresponds to 9, and so on. We can edit our lists by going to Stat, Edit, and entering our values into list 1 and list 2. Let's look at these data values in a scatter plot. We can do that by going to Stat Plot. We'll press second and then the Y equals button for Stat Plot. And notice that Plot 1 has List 1 and List 2. We want to turn that one on. So pressing Enter while Plot 1 is highlighted and changing that to on, we'll plot the data values from List 1 and List 2. Next, we want to make sure that our graphing screen is zoomed in appropriately for our data values. And we can do that by pressing Zoom and then option 9 for Zoom Stat. That will zoom the window based on the statistics that we have in our lists. Looking at the scatter plot, it's hard to tell if there really is a linear correlation or not. It's such a small sample that it's difficult to tell. But if there is a linear correlation, can you tell that it would be a positive linear correlation? Now we'll use the function linreg t-test to calculate R. We'll go to Stat, toggle over to Tests, and scroll all the way to the bottom and find linreg t-test, option F. Since our data values are in list 1 and list 2, we will enter list 1 by pressing second 1 and list 2 by pressing second 2 for X list and Y list. We're not going to worry about these other details for now because we're not conducting a hypothesis test. We simply want to calculate R. So when calculate is highlighted, we'll press enter. Linreg t-test gives us a lot of information. Scrolling down a ways will give us our value for R. R in this case is 0.795 when rounded to 3 decimal places. Using our calculator function, linreg t-test, we found that R is equal to 0.795. So on the scale from -1 to +1, we are somewhat close to +1, which might lead us to believe that there's a positive linear relationship here, a positive linear correlation. But what is high enough? What is close enough to +1 to say that there is a positive linear correlation? That's where a hypothesis test and significance level comes in. So we'll talk about that next. When we're running a hypothesis test regarding linear correlation, our H0, our null hypothesis, is that rho is equal to 0. That corresponds to the idea that there is no linear correlation. The alternative hypothesis will always be that rho is not equal to 0. We have sample data that pulls us far enough away from 0 to say that there is a linear correlation. That is, if our sample data pulls us far enough from the center of 0, we will have enough evidence to reject the null hypothesis and support the alternative. We can run a hypothesis test using the p-value method or the critical value method. With a significance level of alpha, if the p-value is less than or equal to the significance level, we reject the null hypothesis and conclude that there is sufficient evidence to support the claim of a linear correlation. And if the p-value is greater than the significance level, then we fail to reject the null hypothesis and conclude that there is not sufficient evidence to support the claim of a linear correlation. With the critical value method, we are comparing R, the linear correlation coefficient, to the critical value. If the magnitude of R, or the absolute value of R, is greater than the critical value, we reject the null hypothesis and conclude that there is sufficient evidence to support the claim of a linear correlation. But if the magnitude of R, the size of R, is less than or equal to the critical value, we fail to reject the null hypothesis and conclude that there is not sufficient evidence to support the claim of a linear correlation. Let's get started with an example. In this example, our job is to determine if there's a linear correlation with this paired data. We're going to use a significance level alpha of 0.05. Let's start by putting the first row of data into list 1 and our second row of data into list 2. Going to Stat and then Edit, we'll start by clearing out the old data to make room for our new data. Let's also take a look at our data on the graph as a scatter plot. Going to Second and Y equals will get us to the Stat Plot menu, and Plot 1 is still turned on with List 1 and List 2. So now we'll press Zoom and then Option 9 for Zoom Stat. Taking a look at this scatter plot, it doesn't appear that there's a linear correlation, but we won't know for sure until we run the full hypothesis test. Looking at the data like this first will give you some intuition about the results before you run the test. That way, if your test contradicts what you thought should happen, you know that you should probably double check something. Let's head back to our example. The first step in the hypothesis test is to determine the null and alternative hypotheses. For this type of hypothesis test, the null hypothesis is always that rho is equal to 0, and the alternative hypothesis is always that rho is not equal to 0. The null hypothesis corresponds to there being no linear correlation, while the alternative hypothesis corresponds to there being a linear correlation. The second step is to calculate R, and we can do that using our calculator function. We will go to Stat, Tests, and towards the very bottom, we want linreg t-test, linear regression t-test. We'll make sure that we have list 1 for XList and list 2 for YList, leave the frequency at 1, and we'll select not equal 0 to represent the alternative hypothesis that rho is not equal to 0. Once calculate is highlighted, we'll press enter to run this test. Scrolling down a little bit, we find that R is equal to 0.022, and towards the top, we find that our p-value is 0.9512. We're also going to need that for step 3. So let's take those values back to the example. Using linreg t-test, we found that R was equal to 0.022, which confirms our intuition looking at that scatter plot. This value for R is pretty close to 0, which would indicate that there's no linear correlation, but we'll still continue the formal test. With step 3, we want either the p-value or critical value. Even if you're using the p-value method, looking at the scale from -1 to 1 and comparing the critical value to R is really helpful to understand the meaning of these values. Our linreg t-test gave us a p-value of 0.9512. Let's also take a look at the critical value. Looking at the table of critical values of the Pearson correlation coefficient R, we can find our value for n, which is 10, and our value for alpha, 0.05. Where these two meet up is our critical value. Let's put this critical value on a number line and compare it to R. Remember that R ranges from -1 to +1. We found a critical value of 0.632. On our scale from -1 to +1, this critical value and its negative counterpart serve as the barriers for how close to -1 or +1 our correlation coefficient would need to be in order for us to conclude that there's a linear correlation. If our value for R landed in either of these regions towards -1 or +1, then we could conclude that there's a linear correlation. But our value for R is 0.022, which is nowhere near these regions. The size of R, or the magnitude of R, is not larger than the critical value, so we fail to reject the null. So either way you look at it, using the p-value and comparing it to alpha, or the critical value and comparing that value to R, our conclusion is the same. We fail to reject the null. And in failing to reject the null, our conclusion is this: there is not sufficient evidence to support a linear correlation. Let's take a look at another example like this one. In this example, we have a new set of paired data, and this time our value for alpha is 0.01. Once again, let's start by putting these values into our lists, list 1 and list 2, and we'll look at the scatter plot to get a heads up on if there is a pattern. We'll go to Stat and Edit. To edit our lists, we'll enter the first row of data into list 1 and the data from the second row into list 2. Now we'll go to Zoom and option 9 for Zoom Stat. This picture looks a lot different from our last one. These seem to have some type of linear correlation. They seem to be following a line, and we could pretty well approximate it with a straight line. Let's head back to the example and prepare to run our hypothesis test and see if that hypothesis test confirms our instincts. The first step is always to determine the null and alternative hypotheses. The null hypothesis for this type of test will always be that rho is equal to 0, that there's no linear correlation. And the alternative hypothesis will always be that rho is not equal to 0, that there is a linear correlation. The second step is to calculate R. We can do that using our calculator or by hand using the formula. Let's head back to our calculators. Now we'll go to Stat, toggle over to Tests, and go to the very bottom for LinReg t-test. Our data values are found in list 1 and list 2, and this is still set to not equal 0, like we see in the alternative hypothesis. When Calculate is highlighted, we press Enter. Scrolling down, we find that our R is 0.987, and towards the top is our p-value of 1.33 times 10 to the negative 7th. Let's take those back to the example. We found our value for R to be 0.987. That's awfully close to +1, which confirms our instincts when we looked at that scatter plot and saw this shape of a line that went up as we moved from left to right. The third step is to find the p-value or critical value. And again, I'm going to do both because I think it gives us a really good understanding of the meaning of R. Our calculator gave us a p-value of 1.33 times 10 to the negative 7th. That's 0.000000133, which is an extremely small number, much smaller than alpha. Let's head over to the table to find our critical value. We again happen to have an n value of 10 because there's 10 pairs of data. This time though, alpha is 0.01, which gives us a critical value of 0.765. The size of R would need to be at least 0.765 for us to support a linear correlation. We found our critical value to be 0.765. We used n equals 10 and alpha equals 0.01. Let's look at these values on our scale from -1 to +1. With our critical value equal to 0.765, 0.765 and -0.765 serve as our thresholds for what is good enough or close enough to -1 or +1 to be considered a positive or negative linear correlation. The value for R that we got from this data was 0.987, which this time is higher than the critical value. The size of our value for R is greater than the size of the critical value. So this time we're going to reject the null. Whether we compare the p-value to alpha or look at the location of R in relation to the critical value, we come to the same conclusion. We reject the null hypothesis. In rejecting the null hypothesis, our conclusion is this: there is sufficient evidence to support a positive linear correlation. Notice that the alternative hypothesis is simply that there is a linear correlation, but given that we have a value for r that is positive and very close to +1, we can make an even stronger statement supporting a positive linear correlation. That concludes this lecture video where we learned about linear correlation. We used the Pearson correlation coefficient along with our hypothesis test to determine if we could support a linear correlation in a given set of paired data.